So to help you graph logarithmic functions, remember that if y equals log base a of x, then a to the y equals x. So to graph the logarithmic function, you want to choose values for y, or f of x, and then compute your values for x. You want to plot the points and then connect the points with a smooth curve. So we're going to graph the following. We're going to do f of x and g of x. Now, f of x and g of x are inverse functions to each other because log base 2 of x is, its inverse is 2 to the x, right? This is how we solve each other. So if I focus first on f of x, now if we think about powers of 2, okay? If I were to raise, and it might be helpful, I guess, to look at the g of x function. Okay, so if I raise 2 to the negative second power, that's 1 over 2 squared, which is going to give me 1/4. Okay, and if I raise 2 to the negative first power, that's 1 over 2 to the first, which is 1/2. And if I raise 2 to the 0 power, anything to the 0 power is 1. And 2 to the first is going to be 2. And 2 to the second is 4. So that's looking at 2 to the x, right? So going backwards to its inverse, I now want to pick values for the outcome, right? Because we're undoing this. So if I pick these same outcomes that are over here in the x column for the f of x column, and I say log base 2 of negative 2, remember what we're saying is if I were to raise 2 to the negative second power, what would it equal? And therefore, it would be 1/4, because if I did log base 2 of 1/4, I would get negative 2 back. Okay, if I do log base 2 of something and I want it to equal negative 1, well, log base 2 of 1/2 equals 1. And log base 2 of something equals 0 is 2 to the first power, or excuse me, 2 to the 0 power equals 1. And log base 2 of something has to equal 1. Well, the only way I can get 2 to equal itself with the first power is 2. So log base 2 of 2 is going to give me 1. And then 2 to the second is going to give me 4, meaning log base 2 of 4. And again, if you think about this, it can be helpful to switch it from logarithmic form to exponential form, which would be 2 to the f of x power equals x, which kind of gives us that idea that if I'm trying to raise 2 to something and I want it to equal, if I'm raising 2 to the f of x power, so 2 to the second, and what is it going to equal? 4, which is why we consider choosing our y's first and going backwards. So if we graph these, I'm going to graph my f of x in green and my g of x in blue. So x being 1/4, f of x is negative 2. Okay, x is 1/2, f of x is negative 1. X is 1, f of x is 0. X is 2, f of x is 1. And x is 4, and f of x is 2. Okay, so we get this curve that's going like this. Okay, that's my logarithmic curve. And now if I graph my g of x curve, which is just my normal exponential curve, I go to negative 2 for x, y is 1/4, or g of x, excuse me, is 1/4. X is negative 1, g of x is 1/2. X is 0, g of x is 1. X is 1, g of x is 2. And x is 2, g of x is 4. And I draw this curve. And if you remember from our work at inverses, an inverse is a reflection across the line y equals x. And you can see that if I were to draw that line y equals x through here, and I would fold the whole graph along it, the blue and the green curves would end up matching up. And again, that's because they are inverses of each other. So the last part says identify the domain and range for each. So if I look at my f of x curve, the domain there, and that's the green curve, clearly my domain is from 0 to infinity for x values. We can see that x cannot go below 0. And the range for that, though, y extends into infinity, so the range is going to be from negative infinity to positive infinity. Okay, so this is my f of x curve. Okay, and for g of x, because I'm running out of room, g of x is the blue function, right? The domain there is from negative infinity to positive infinity for the x values. And then the range is from 0 to positive infinity. So I want you to see that when we compare a function to its inverses, the domain and range swap between the function itself and its inverse.